Okay, so we left off yesterday. We're talking about IMF, ideal gases, kinetic molecular theory. And Emin, would you please explain to us this practice problem, which is, by the way, a common FRQ? Like, if we got data that was not what we expected, why might that be the case? So, Emin, what did you say?
Okay, so let's say you took your gas sample like in a container or whatever, and then the fact is that when you have a IMFs, some of them are attractive, right? So then it means that there are less collisions, or fewer, and the collisions that do happen are less forceful against the walls, and that results in lower pressure. And PV equals NRT is our equation. That volume will also follow lower pressure.
Okay, so we have the real gas sample experiences attractive forces such as IMFs, which cause inelastic collisions, which in turn reduce pressure and volume. All right. Great. Awesome. That's one way to answer it. You could word it slightly differently, but the big idea is yes, you should tack on or cling on to the concept of IMFs as the big reason. Yes, Alok.
Are IMFs causing inelastic collisions or are they separate things?
They're connected. Yeah. So now that we've kind of done that super brief overview, because we just low-key kind of ran out of time yesterday, and I wanted it as a warm-up. Now we're going to transition to the third subtopic within Unit 3, which is solutions and mixtures, which, by the way, is all about interactions between molecules. It just feels like another subtopic, like its own thing, just because it doesn't seem to flow from gases to solubility. Like it just kind of doesn't seem to flow, but it really is connected because it's all about not bonding, but engagement and interaction between molecules. No bonding is actually happening between any of these topics. Okay, so one thing that you should remember is from Unit 1, solute, solvent, homogeneous mixture versus heterogeneous mixture, physical techniques for separation, and so forth. Okay, we're going to take a focus on homogeneous because remember, homogeneous mixtures are called solutions. Okay, you can't really tell the components initially apart. Yes.
What's the distinction between a really strong IMF and a bonded?
An IMF produces no new compounds, and a bond produces a whole new compound with whole new physical features and characteristics.
Is there anyway, like, could a really strong IMF have bonds? Or
No. But we do say ion dipole attractions are this weird combo of the two. And even though it's technically a type of IMF, and then hydrogen bonding is such a strong interaction that it almost acts like a bond because it's so hard to break. Your hydrogen bonding, when you look at the structure of your like DNA molecules, the phosphate groups are engaging in hydrogen bonding across the spirals, which is why it's how they stay connected. So they're really powerful. They're no small thing to be trifled with. Okay. So then we're just going to move forward and assume that you kind of know that basic information from Unit 1. And what we say is that for a solution to occur, for a mixture to occur at all, for a homogeneous mixture to occur, what you have to have is the attractions between solute and solvent must be greater than the attraction between solute and solvent particles, right? So it must be favorable for some reason for your solvent to now attach in an interaction, not a bond, but attach or interact with your solute now. Because remember when you mix two things, right? They're all in a sample together. They're all clinging on to each other. So if you want a homogeneous mixture, a relatively even distribution, you have to create a connection between the two parts. Okay. So we say this should be reviewed from Unit 1. Things that are miscible, particularly liquids, okay, that are soluble or mix, right, well, are miscible. Immiscible are liquids that aren't, okay, soluble. Okay, don't mix. The reason I add this is because you can say something's soluble. Another way of putting it is insoluble. You can say something soluble or not soluble. But when you say miscible and immiscible, you are specifically talking about liquids. You can say soluble, insoluble for gas state, solid phase, anything. But miscible is particularly used terminology for liquids. Okay. But of course, the word soluble and insoluble applies to anything, right? Okay. So this brings us now to the topic of how do we measure how something soluble is? Because honestly, simply saying something soluble and insoluble is very, very vague. But we need to actually quantify it. So we talk about, we talk about it in terms of solubility. Solubility is like the verb of it. Okay. So solubility at a given temperature. Notice, solubility does change according to temperature. You should notice that. It does change according to temperature. So at a given temperature, it's a measure of the maximum amount of solvent, okay, that will dissolve in a given amount, solute, that will dissolve in a given amount of solvent. So it's the measure of the maximum amount of solute that will dissolve in a given amount of solvent. Okay. And again, it is temperature dependent. Okay. That's going to become very important later. So the units for solubility tend to be molarity. How many moles of the solute can dissolve in how many liters of solvent? Okay. Or we also sometimes do grams per liter. Okay. That tends to be a common one too. We're going to focus on molar solubility or solubility measured in molarity. Okay. So we call this, just to be clear, molar solubility value. And that is the solubility units in molarity. That's all it's saying. Kind of like saying like molar volume or anything, just like a unit measured in molarity, particularly to one concept. Okay. So, the solubility of calcium sulfate is 1.1 grams per liter at 25 degrees Celsius. Calculate its molar solubility. So like, honestly, this shouldn't be too bad. 1.1 grams per liter times, well, I just need to get to moles per liter. So I simply use the molar mass of calcium sulfate, which would be 136.1 grams. And it should end up being the molar solubility is 8.1 times 10 to the negative 3 molarity calcium sulfate. So this would be the maximum amount of solute that could dissolve in 1 liter at 25 degrees Celsius. This would be the maximum solubility value in molarity. This would be molar solubility of calcium sulfate at 25 degrees Celsius in whatever liquid we're talking about. And my guess is it's aqueous because we tend to dissolve all ionic compounds in water. This just kind of is our thing, right? Because remember, ionic compounds dissociate in water. So they keep their ionic nature, they just separate. But they keep their ionic nature. They don't suddenly go to a neutral form. So they still keep some of their properties, which is great. So go ahead and try practice 2 and 3 on your own. And then we'll quickly compare. So Sam, what'd you get for practice number 2?
I have no idea.
Oh. Okay. Does anyone know? What's your guess?
I would assume we have to take the 15 grams over 0.225 liters and then multiply it by 1 mole over the molar mass of sodium hydroxide, which is 35.
Yeah, so okay, so let's just pause for a second. Malcolm's thinking is right. What we see is we get 15 grams of sodium hydroxide. Okay, and we're dissolving it to its maximum solubility level in molarity. And what we're trying to find is what's the value of that then in molarity? Well, we're told that 15 grams dissolves in 225 milliliters. So we know that somehow we need to convert this to moles per liter. So your first
25 milliliters is the water, like whatever is being like dissolved in, plus.
We're assuming that the contribution of the solute is very minimal to the overall liter value of solvent. Yep. So, because you're not really pouring in two liquids, right? If you added two liquids, then you'd have to account for dilution. But since it's a solid plus a liquid, we just take the liquid's value as the general amount of solution. So that's a good point though, because that will matter later. So then what you do is you do a dimensional analysis. So what Malcolm was saying is, yes, you need to convert. Okay. So you need to do one for every, for every 1 mole of sodium hydroxide, it's what? What's the value? Like 44 point something? 16 plus H 17 plus 23. Yeah, it's about 44 grams. Okay, for sodium hydroxide. And then you need to convert from 1,000 milliliters to liters. And you should get a value of, did anyone get the value? Okay, but around what?
Well, like, sorry, I forgot to multiply that. 2,666.
Ooh. Ooh. I don't know about that one. You got 40 grams for the moles? For the molar mass? Okay. Man, I'm going straight off of memory here, so I don't know. 40 grams. Okay. So then you got, what was your value? I got something around 1.67. Good, good. And if you're to the correct sig figs, what is it? Excellent. Molarity. Good. So practice number 3. How many moles would we need to create 2 liters of a 1.5 molar solution? Well, you know that 1.5 molar solution is like saying moles over liters. And the question is how many moles for this amount of liters would get me to that same value. And what you do is you simply solve for the unknown. And you should get that you should have about 3 moles of solute. Okay, whatever you need in 2 liters to get a 1.5 molar solution overall, right? You're just solving for the unknown. Do not forget to look at molarity as moles over liters, because oftentimes when you're doing math, that's actually the best way to look at it. So yeah. Okay, good. So when we talk about molar solution, we can categorize, because remember, technically molar solution or molar solubility is just a measure in molarity. But then we have this concept of, well, what does that value represent in terms of the degree of solubility, the degree of dissolving that's happening? So what we see is that, generally speaking, we call a substance that has more than 0.1 mole of solute dissolve in 1 liter, we call it generally soluble. We're looking at ranges. If it falls within this area, we would call this soluble. If it has a molar solubility value that's equivalent around this, it's soluble. If, of course, we have less than 0.1 moles of solute dissolve, okay, we have low, okay, solubility. This is kind of very generic terminology. This really is just terminology for you at this point, okay? And then finally, of course, if nothing dissolves, right, like metal and water, metal doesn't really dissolve. Insoluble, okay? So that's kind of how we use some of those values to create a range of solubility terminology. So when we think about, oops, I don't know if I want to write that. When we think about molecular solids, okay, and being soluble, we've already kind of talked about ionic compounds being soluble. They have this unique ion dipole attraction, right? But when we think about molecular solids that are totally based off of IMFs, don't forget that. These are based off of IMFs. What we say is that when molecular solids dissolve, the IMFs, okay, between the molecule units, the individual molecules, the units of molecules, all right, are broken, okay, and new IMFs are formed between the molecule and solvent. All right. And if you have a value of 0.1 moles of that molecule dissolving in 1 liter, at the very least, at 25 degrees Celsius, we call it soluble. If you have some, but not very much in low soluble, okay? And then of course, if that molecular solid doesn't dissolve at all, you have insoluble. Sugar is a very soluble molecular solid. It's why you pour it in everything, like your coffee, which is an aqueous solution. Okay. There's a general motto when we talk about predicting solubility. Yes, look.
Can you define a molecule as soluble without the solvent in question?
Can you define a molecule as soluble?
Without the solvent, because isn't solubility dependent on the thing you put it in, as in the solution you're depositing it in? And thus, you can't really classify something as soluble or not because that varies.
Well, yes, within the context of solvent. So sugar is very soluble in water. Yeah.
Are we usually working with water? Or is it
Usually, until about right now, when I'm going to tell you something new. So what we have here is, what if you're not always dissolving in water? What if you're just looking in general at general mixtures, whether it doesn't even matter the state of matter, just generally speaking, how can I predict without actually always having to calculate or look at data? How can I predict whether something's going to be soluble or insoluble? Okay, well, there's a little cute model. Okay, it's called likes dissolve likes.
This is an important one to remember.
This is very important. Likes dissolve likes. And what likes dissolve likes tells us is that, let's say I don't have any actual values. All I know is I have characteristics about the two things I'm trying to mix. I know that they're polar and I know that they're non-polar, or vice versa, or whatever. I just know the general polarity characteristic of it. I have no information on the amount, no information on molarity. I just know that this is oil and water. Well, what I say to myself is, well, according to solubility rules and characteristics, similar polarity substances will dissolve or be soluble with, mix well with other similar characteristic substances. So what we say is that polar plus polar will be soluble, but non-polar plus polar will be insoluble, or at least low soluble, insoluble / low soluble. I don't know. I'm just like trying to make it shorter. Okay. So, vice versa could be said, by the way, that non-polar plus non-polar was also soluble. This, by the way, is the principle I mentioned early on with chromatography, why certain samples will travel up with the liquid. And that's one of your AP problem walkthroughs in the next coming days. So this principle explains why oil and water don't mix. Oil is non-polar. Water is polar. They create a heterogeneous mixture, a separated mixture, because they do not have the similar characteristics of polarity. They would demonstrate very low molar solubility. Yes.
Does the polarity of the solvent have to be greater than that of the solute for it to be soluble?
Not greater than, it has to be similar.
Okay.
So as long as your polarity is within a polar range, you're going to get some mixture. But if you've got completely off, the more unlike something is, the more likely it's to separate, not mix well. So you will always have a wee bit of most insoluble things that we see on a naked eye level are really just low soluble. There's actually some solution mixing happening. There's some mixing happening, but there are instances where there's literally no mixture happening. When we mix oil and water, it's called emulsification. And that's not actually true mixture. That's us trapping oil bubbles in water shells. Like, that's not actually mixing. It's just we happen to shove them in to the cracks and crannies of the water molecules. Like, that's it, but it's not true mixture. So there are some things like that that are truly insoluble. But yeah. So going to looking at dissolving ionic solids now we're going to go back and look at this. Okay. We talked a little bit about dissolving molecular solids and talking about this motto, which, by the way, this motto tends to work mainly with liquids to liquid mixtures. This is a great motto for liquids to liquids. It's a little harder to do with like salts and compounds. So that's why we're kind of moving on to now ionic solid, because all of these examples of how things mix kind of have their own unique context. All right, but they all still follow the general rules. Okay. So when we look at dissolving ionic solids, we got to remember that when we dissolve an ionic solid, we're breaking intramolecular forces and we're creating ion dipole attractions, right? Between the ions and the water molecules, the polar water molecules. All right. And so what we say is that generally speaking, a lot of ionic solids are soluble, such as salt, okay, such as CuSO4, such as a ton of your lab solutions are ionic compounds dissolved, dissociated, soluble in water, aqueous solution. But there are instances when we see insoluble occur between the solid and liquid. So this is a solid liquid mixture. Notice that, solid liquid mixture, okay? Kind of like the molecular solid, only it's a different intramolecular force that we're dealing with. And what we say is that sometimes we have, okay, insoluble or what we call a precipitate, a solid salt is formed. And so what we need to do is we need to look at a table that specifically deals with predicting ion dipole attractions formed between ionic compounds being dropped in water. This table, you have to memorize the first 4 rules. The AP also spells it out for you exactly what rules they want you to memorize. My memorization list on my website also tells you, but there's this whole table. You should know how to read it and then also memorize the first 4. And one thing that I saw your hand, I'm just going to ignore you for a second. One thing that you should notice is that when we are dealing with ionic solids and predicting whether they'll be soluble in a liquid, specifically water, we don't really like mix ionic solids in like oil. Like we don't do that. Okay. What we say is, okay, according to this table, any ionic compound with a cation that is an alkali immediately will dissolve in water. Immediately. Like it doesn't even matter what the anion is. It is literally going to dissolve. It's going to be soluble, pretty highly soluble actually. And it's going to create a homogeneous mixture ion dipole attraction filled sample solution. Okay. But if you go down, what you see is that, for example, sulfate, only some things are completely soluble, but other things will kind of actually stay as a solid. If you dropped a sulfate compound in there, that's a salt, a lattice structure with copper sulfate, okay, copper 2 sulfate, it probably wouldn't dissolve very much. You'd have to really agitate it and like really force it to break apart. The ion dipole attractions wouldn't be that great. The solute to solvent attractions wouldn't be that great. It would like to stick with its intramolecular ionic bond, and the water would like to stick with its little dipole hydrogen bonding self. Okay, so you'd see minimal dissociation, minimal dissolving. All right. So something to know about dissolving ionic solids, this solid to liquid solubility, is that when ionic solids do dissolve and release their cations, we get electrical conductivity properties. So this occurs when ionic compounds dissociate. It's a gained property, which by the way is part of the reason why ion dipole attractions are so unique, because most of the time intermolecular forces don't necessarily create new properties. They either strengthen or weaken certain properties. This takes on a whole new characteristic, electrical conductivity, which is an intrinsic property. So this is why ion dipole is another reason why it's so unique. It's this weird mix between an inter and an intra. You don't make a new compound, but yet you get a totally different property once it's dissolved. Again, this is why you're electrocuted in chlorinated water. Yes. Intermolecular forces are the forces between molecules. So ion dipole, hydrogen bonding, dipole, and LDFs, London dispersion. Intramolecular are the forces that hold compounds together. Ionic, covalent, metallic. Molecular solids are based off of sharing of electron compounds, so Lewis structure stuff, resonance. Ionic solids are based off of cation, anion, canceling out charges.
Okay, so it's like bonding
Yep.
between ions.
Yep, it's the type of bonding that's constructing the solid. So, yeah. So this brings us into a little subtopic on electrolytes. We would call any ionic compound aqueous solution that has been dissociated an electrolyte solution, because an electrolyte is any compound or dissolved compound that can carry an electrical current. And if any of you want to find out if water can truly carry an electrical current, go swimming during lightning. Okay. We also say then that, to summarize, all soluble ionic compounds or acids are considered electrolytes. So I mentioned acids a while ago. Acids are a unique type of ionic compound that have an H proton that can leave it. Okay, so HF is hydrofluoric acid or hydrogen fluoride, but it particularly is known for its acidic properties because of that H plus serving as one of the ions, specifically the cation. It would also be qualified as an acid. An acid is a subcategory within ionic compounds. So soluble ionic compounds and soluble acids within that are all considered electrolyte because they all dissociate. They all have now free charged ions running around in the liquid, okay? And they all now can carry a current. So let's turn to how do we quantify this? Because in the end, chemistry is all about quantification too. So let's say I have 0.685 molarity solution of potassium carbonate, aqueous. Oh, if it's aqueous, we know it is soluble, it is dissociated, it is dissolved. How many moles of each ion, cation and anion, are present after dissociation? Well, bing, bada, boom. Let's start looking at our molar ratios. Law of constant composition. Please tell me I was right. Is that the law? Law of constant composition? Yeah, I think so. Is it law of constant composition? Yeah, I think so. So it's 0.685. My voice is never going to heal from Disneyland if I keep talking like this. 0.685 molarity of K2CO3. Well, we know for every 1 K2CO3, we have 2 K plus cations. And for every 1 K2CO3, we have 1 carbonate anion. Okay, so that means if we have a amount, so let's look at the cation amount, cation molarity. If we have 0.685 molarity of K2CO3, that means unit conversion wise, for every 1 K2CO3, I have 2 K pluses, which means I have a molar ion concentration, okay, of 0. Oh, gee willikers. 1 math, 12. Somebody help me. 12, 1.3, help me.
1.37.
1.37. Yeah, Charlie, that's right. You know, I had a pre-professional last year who was like a walking calculator. He was awesome. He was so good. We still send each other memes about teaching. 1.37.
I hope that's right.
Yeah, that sounds about right. 1.37 K plus. Okay. And that's in moles per liter. Okay. So that's in moles per liter, K plus. Now, if you're asking how many moles are present in solution, well, let's just assume I'm in 1 liter. So technically then, how many moles are present? 1.37 moles in that 1 liter. Okay. Next one, anion. Okay. Shouldn't be too bad, folks. 0.685 times, okay, for every 1 K2CO3, I have 1 CO3 anion 2 minus, which means I'm going to have a molar amount or moles in 1 liter of 0.685. Gee willikers. 0.685. Why does my handwriting get so bad? 0.685 molarity or moles per liter of carbonate anion. Okay. And those are my answers. And if you're like, wow, that really felt like I didn't need to learn everything beforehand. No, well, here's the thing. All of that beforehand is telling you how we even study these circumstances. It's kind of pointless to quantify a context that you don't really understand why it's working and how it's happening. But in the end, what we then do is we use that context to understand the problems that we have to then quantify and put a value out for. And also notice something. You're using molar ratios based off of the subscript ratios, right? For every mole of this, if I have 2 things in it, I'm going to get double that many of those little parts, components. So you're starting to notice that the mole is still a continual concept that we use for comparison and ratio. Don't forget that. Okay. So, and I started filling this in because I knew I was going to want to break from handwriting. So the next thing I want to talk about is acid-base conductivity, because I mentioned earlier, okay, acids are also electrolytes. Ooh, okay. So when an acid reacts with water, we say it produces an H+ ion. And we'd say that a strong acid, by the way, is able to completely ionize. By completely ionize, I mean it loses all H+ ions, okay? Separates from them. And then a base can also be considered an electrolyte, by the way, because a base either produces a negative OH ion or it's able to accept an H+ ion. And we say for complete ionization, it does this it does it fully. That's the big idea, is it interacts fully with the ions. And that's kind of the last thing I wanted to mention about acidic/basic conductivity. These both are forms of ions, ionic compounds, that have freely charged things floating around that can conduct electricity as a result. Okay. So obviously then, when talking about electrical conductivity and quantifying the amount of ions present, we see a relationship that the more, did I want to say the word more? Okay. Ionic compounds are electrolytes. Oh, all ionic compounds are electrolytes, but not all are easily soluble. Okay, the greater the electrolyte, the more ions, the greater the conductivity. The weaker the electrolyte, the less ions, the less the conductivity. So for a K2CO3 ion, you have more ions being produced, 2 moles of K and 1 mole of carbonate, compared to an HF ionic compound, which is only 1 mole of H, 1 mole of anion. You would have greater, theoretically, conductivity because more ions are being produced, which you then could quantify using your molar ratios revealed in the subscripts. How you doing? We're doing okay? It all makes sense later when you go home and you don't have my voice. Yeah, yeah. The stronger the electrolyte, you have more ions. Gatorade is ionized water. It's flavored ionized sugary water. It's K+ ionized. They help with your ATP pump. So biochemistry. Yeah. Alok. An electrolyte is a compound that can create electrolytes, which are free ions. So, all right, we're not done, folks. We're not done. So, we got a little bit more to go. Not too bad. So this stuff we can whip through. This stuff will make a little bit more sense. So how do we increase solubility? Okay. So increasing solubility. What if I have a low soluble thing and I really need it to be soluble? I really need my electrolyte to dissolve. I really need my maximum amount of ions in solution. I really need a fully saturated solution. I need my ionic compound to break down. Well, here's something to remember. Solubility depends on temperature, And what was the other word I was gonna say? It depends on, I think I moved some things around, so I'm trying to. Gee willikers. No, it says it depends on blank of, oh, character, nature of solute and solvent and the temperature. Okay. So when we talk about increasing solubility, and I don't know why I wrote in green. When we talk about increasing solubility, there's a couple ways that we could do it. Okay. One, you can increase temp. Better, higher temps, usually more increase in solubility. Okay. Usually. You'll see that it doesn't apply to gas some mixtures. Shocker. Okay, you can increase through agitation. You can increase agitation. By agitation, I mean stir the darn thing, which you guys already kind of know. It's if you're protein, I don't know how many of you guys go to the gym, but last group I had, they really were gym rats. Okay, if you increase your protein powder, or I take a fiber powder every morning, I take a fiber powder. Do you know what a gym rat is? It's like those guys that are like, you know. So if you have like, I have a fiber powder in the morning. Okay, I don't take a protein powder because I'm not about that, but I have fiber powder and it doesn't mix very well. It's low solubility until I stir that sucker up. Okay, I agitate those molecules, and what I can do is I can increase the collision between the solvent and solute that create more attractions to create more solute-solvent IMS forming, breaking up the solute-solute, breaking up the solvent-solvent. And I can create like a pseudo greater solubility. Yes.
You increase temperature when you mix it up. That's how.
Oh, well, you increase the kinetic energy. Theoretically, I don't know about temperature. I think it's still. Ooh, that'd be interesting. Technically, I guess at a microscopic level, there'd be a slight increase in temperature. But I mean, I just like shake the thing.
Would you also increase surface area? I guess.
Well, you can. So that's the other thing you can do is you can increase the surface area.
But like by strength.
You're creating the effects that increased surface area would give you. And because increased surface area means you get more potential interactions. Right? So like in a room that's well spaced out, okay, you're likely to be able to freely encounter someone else. But if you're pushed up sardine style, okay, in a crowded room, you're never going to go see that person on the other side because you can't move. Your likelihood of interacting is much smaller. Okay, that's kind of the best way. Increasing surface area is particularly valuable for like solid involving mixtures, solid to liquid, solid, stuff like that. The fourth thing that you can do is, what's the fourth thing you can do? I'm trying to remember. This doesn't seem, oh, you can increase the pressure for gas solutions. For gas only solutions. So I should say gas involving. A gas to a liquid, gas to a solid would be a weird mixture. And then a gas to a gas, okay? So that's some ways you can increase solubility. Now, depending on the level of solute, we have another way to categorize solubility through different terminology. Yes?
Why would a chemist want to increase solubility?
Because sometimes we need things to mix. Because that's what we need for the reaction.
Okay, to create a reaction.
Probably. Or create the environment for a good reaction. Yes?
Will things eventually mix without agitation or without these structures, or can they just like stay in there?
I mean, they'll eventually mix at some point, but oftentimes you don't have the time to wait. Time is money, man. When you're doing research, I was running 4 or 5 different, I was starting 4 to 5 different reactions, and then I was purifying 4 to 5 different reactions that I started the previous day. And then I was analyzing the 4 to 5 reactions that I started the day before that. No time to waste. So the faster we can increase the process, the better. The more money we make, the more likely we're going to get another grant. Purely from like a time is money perspective. Yes. Kinetic control reactions, awful. Unit 8, when we talk about Gibbs free energy and how to predict spontaneity, there are some really, really, really slow reactions that we call kinetically under kinetic control that are, even though they're spontaneous, they occur at a super slow rate, like turtle level slow. Okay, So let's talk about another way that we can categorize and label solutions. We could say that a solution, okay, and here we're assuming it's soluble. So these are all terms assuming solubility, assuming a soluble mixture between two things. So now that we're soluble, now we can categorize, well, how maxed out am I in soluble? So a saturated solution is the max amount of solute that can dissolve. It's often quantified as the molar solubility, even though technically molar solubility is just solubility measured in molarity, but we often call it the molar solubility that's associated with saturation levels. Max amount of solute, solute, okay, that can be dissolved in solvent. Okay, now what if, yes?
In the case of ways to increase solubility, if solubility is defined as the amount of solute that will dissolve in the solvent, wouldn't those only increase the reaction time and not the actual quantity of the
No.
amount?
Think about, again, your powders. You could, I mean, like, yeah, your suspicious powders. Yes and no. Because sometimes without that, it would just stay. Like, there's not enough collision that could happen without the assistance to make it go past insoluble or go past low solubility, no matter how long you let it rest. So unsaturated is, okay, I have a soluble mixture. I didn't put enough solute in. Like, I literally have more space for solute. So an unsaturated solution is between a soluble components, but it contains less than the max. And then supersaturated solutions are, okay, contain more than max. So what we see is, so solute precipitates out. And by precipitates out, how do I spell precipitate? Precipitates, precipitates out. And by that, I mean literally solid chunks form. So, okay, this I definitely forgot about there. But anyway, okay, this right here is a supersaturated solution. If I were to heat it up, it will dissolve. But as it cools, I have way too much solute in here that as it cools and it doesn't have that oomph of pseudo solubility, it will saturate out. So there's still some dissolved solid in here in that liquid portion, but it's so excess filled. It's literally drowning in solid. So what happens is we go past solubility and we get undissolved crystals, even though technically the compound that you're looking at is technically soluble. You just reach max capacity for that amount of solvent to be able to handle it. Okay? Totally forgot about this. Okay. Wow, I didn't got everything else to like heat it up, show you. Gee willikers. Okay. So what we have is we often graph little charts called solubility charts. And the big idea here is, how do you read them? So we often look at grams of solute per 100 grams of solvent, which is usually, by the way, water is usually the solvent that we're in. They'll specify otherwise. And what we say is, for a given compound, if you're above the curve, you're super saturated. You have way too much solute, super saturated. You have way too much solute despite being technically soluble. You just max it out. If you're on the curve, you're at max, okay, dissolving. So we called it saturated levels. And if you're below the curve, you're unsaturated. These are the dream FRQs. Like, read what's on the curve. Am I saturated or unsaturated? What's the value? Okay. These are the dream FRQs. Yeah. Okay. So, something to note is that all the ways that we increase, all these techniques of increasing solubility and making more solute fit in there, they all increase the number or frequency of collision between the molecules of solute and solvent. Okay? So, precipitate is just a fancy way of saying that a solid ionic compound has formed. A solid ionic compound has formed that's insoluble. That's just a fancy way of saying it. So oftentimes in equations, what we do is we label it as state of matter, parentheses S as the precipitate, and this is the dissociated, aqueous. That's all I wanted to point out really quickly if it wasn't already clear enough. Okay. So last thing. Okay. Gas solubility. Gee willikers. Okay. What about gases? Gases are weird. Okay. So gases, man, those singing Valentines really took up some time. Okay. Gases have kind of the actual opposite reaction to ways to increase solubility. So the solubility of gases in water increases with increasing mass of the particles and increasing surface area. The larger the molecules, right, you have more polarizable electrons, allowing for more LDF interactions between the gas molecules and whatever else it's interacting with, such as water or another gas molecule, right? So when we look at the effects of pressure on a liquid solid solubility, okay, what we see is that this is kind of like a summary. Okay, what we see is pressure will not have any effect on a liquid solid solubility interaction, but with gases, it increases the solubility. Because think about it, if a gas is volatile and it goes, floats up, you want to keep that sucker down, okay, to create a mixture. If your component's always flying away, you ain't got no mixture, you got a lonely little something, something. Okay, I don't know what it is, liquid, maybe it's another solid, I don't know, maybe it's another gas particle, okay? But you ain't gonna keep them together. Okay, likewise, the effect on temperature on a liquid solid solubility, we've said increases the solubility between a liquid and a solid, or two solids, theoretically. Okay, not really, but like it's mainly between a liquid and a liquid, or a liquid and solid. Okay, but with temperature involving a gas mixture, a gas component, you raise the temperature, you raise the kinetic energy, you raise those suckers leaving you. So what we see is it decreases solubility and when you involve a gas. So gas solubility depends on temperature indirectly. It's an indirect relationship, and pressure directly. Or I know you guys sometimes call it positive and negative. Okay. So, I think I'm actually going to not talk about this. There's an AP problem in your video tonight or tomorrow night that talks about this lab method called titration, where we use certain solutions with certain molarities to calculate unknown solution molarities. I think I'm going to hold off on this and talk about it another day because it's not essential for you to understand. It's more just like, here's the context behind the lab setup. Okay. But I think we're going to be okay without telling you this. So I'm going to stop here. Am I going to regret this? I'm going to regret this. So one final thing, when we talk about solutions, there's a lab method called titration. Titration is what we call quantitative analysis method that's used to determine. I really need to drink more water. That's used to determine. Yeah, but hold on. I don't have time to pee. Okay, is used to determine the concentration, which by the way is molarity, right? The molarity of an unknown substance. Okay, By reacting it with a known substance. By reacting with a substance of known molarity. Okay. So you're gonna do quite a few of these post AP exam, but the big idea is that this is really has to do with acid-base reactions. That's a whole topic in itself. I'm not really gonna get into that, but what I want you to know is that we deal with calculations where we say that however much it took for me to react the unknown sample with the known sample, I can calculate the molarity and the mole value and the amount from that. So that's the big idea, is that equivalence point is the point at which we fully react. And depending on the change or the amount, okay, so we can use the amount of known liquid molarity used to calculate the unknown molarity. Okay, to calculate the unknown molarity. So what you're gonna see is in some of the example problems later tonight and tomorrow is that you have a situation where you have titration and from titration, you're using the concept of moles and molarity to calculate an unknown moles and molarity based on the ratio that they react in. That's all. Trust me, you're going to get a lot more detail later. I just realized that might help you understand one of the AP questions from a very conceptual point of view. But really, the math is the focus, not you understanding this method yet. Okie dokie, artichoke. Good job, you guys.